Нажимать надо на что-нибудь, а остальное все. Хорошо, ладно.
Good morning, ladies and gentlemen, dear participants of the conference. You know, this year, we decided to launch the conference a bit unusual way. That is to add some artistic dimension to the conference. So please meet Angelina Kuzmina and her golden saxophone. And now we can start talking about serious things. So some of you, I believe, remember that we started this conference 4 years ago. At that time it was a pretty small event, about 40 papers presented. This year we have a much bigger conference with two venues, one here in St. Petersburg at the premises of St. Petersburg Electrotechnical University, and another part of the conference, another venue is in Moscow, Moscow University for Electronic Technologies. And the figures are, this year we got more than 300 applications for presentations of papers for this venue, and about 250 papers presented to Moscow. So you can compare the growth of our results. And it's my pleasure to tell you that this time, for this part of the conference, we have speakers from more than 30 cities in Russia and from 10 countries, which is also, I believe, a very good result. I will stop talking serious things at this moment, and it's my pleasure to give the floor now to Dr. Mikhail Shestopalov, the Vice Rector for Research of this university, and also the newly elected Chair of the IEEE Russia Northwest Section. Welcome.
Ну, уважаемые коллеги, друзья, я позволю несколько слов сказать на русском языке, но для наших коллег переведут. Наверное, это будет, скажем так, единственное исключение. Остальная конференция будет проводиться, конечно, на английском языке. Ну, когда я шел сегодня на работу, у меня было хорошее настроение, потому что я знал, что сегодня 1 февраля, у нас особый день в нашем университете, открывается прекрасная конференция, на которой мы сейчас присутствуем. Сегодня через час открывается у нас конференция профессорско-преподавательского состава, куда приедут ведущие зарубежные ученые, выступят наши ученые. То есть, на мой взгляд, это такой замечательный, яркий день в нашем университете, ну, от которого только поднимается настроение. Так, давайте в таком режиме.
Ladies and gentlemen, I'm very happy to welcome you here at this conference, and if you'll allow me to say a few words in Russian, this will be the only exception, and the rest of the conference will be held in English. Today, as I was getting to work, I was in a very good mood, because I knew that today is a very special day at the university, the 1st of February, a day when we have two conferences, this one, and another conference of teachers and professors held here. So it's indeed a very happy and interesting day here at the university.
Ну, а прозвучавшая инструментальная композиция, на мой взгляд, только не что иное, как поднимает еще настроение и делает нашу конференцию молодых ученых, молодых инженеров, только лишь еще более привлекательной и красивой.
And I believe that the music we have just heard makes the conference even brighter and even still more wonderful. And as a conference for young scientists, young researchers and engineers, I believe it should be this way.
В своем небольшом вступлении Сергей Олегович отметил специфику именно этой конференции, что мы работаем вместе с Москвой, вместе с МИЭТом, где также проходит и нас, насколько я знаю, транслирует, ну, по крайней мере, в интернету. В одну сторону нас видят москвичи, очень приятно приветствовать их, и мне кажется, расширение границ нашей конференции – это только позитивная составляющая развития сотрудничества.
As the previous speaker has noted, this conference is not only held in St. Petersburg, it's a very broad, wide conference. It's also held in Moscow Institute at the same time. And if I'm not mistaken, our conference right now is being broadcast in Moscow. And I'd like to greet our friends in Moscow and to say that I believe that this expansion, the fact that this conference is both international and all Russian, is a very positive thing.
У нас много проходит конференций в нашем университете, и мы стремимся к тому, чтобы проходило как можно больше конференций. Но мне кажется, данная конференция является в определенном смысле особенная, ну, поскольку участвуют именно молодые ребята, которым есть что рассказать, которые обмениваются мнениями, результатами работы своими, и тем самым обогащают свой научный потенциал, научный багаж.
We here at the university hold a lot of conferences, and we are very proud of that. But I believe that this specific conference, the IEEE, is very special for our university because it's dedicated to young people, young researchers. I believe that these young people, you have a lot to say, and that the conference is a very good way to share experience and compare research and to develop your scientific abilities.
Поэтому, открывая данную конференцию, мне очень хочется поприветствовать всех коллег, как из России, так и прежде всего из зарубежных стран, которые приехали к нам сюда, которые выступят с докладами, и пожелать всего самого-самого наилучшего. Успехов вам!
At the opening of the conference, I would like to greet all my colleagues from Russia and especially my colleagues from abroad, and to wish everybody the best of luck and success.
Считаю конференцию открытой.
The conference is now open.
Thank you, Mikhail. And now it's time for me to give the floor for the plenary presentation. We have one presentation today, and the speaker is Dmitry Holodnyak. Welcome him.
Mr. Chairman, thank you for introducing me. So, ladies and gentlemen, good morning. My name is Dmitry Holodnyak. I can't play saxophone. My major is microwave microelectronics. So I'm going to tell you some things about metamaterial transmission lines and their applications. But I know that the most of you are not quite familiar with the area, so I will tell about some basic things. This is the outline of my presentation. I will start with the introduction about the electromagnetic metamaterials, and then I will show you some basics of the theory of metamaterial transmission lines, and then I'm going to show you the applications of the metamaterial transmission lines to design the advanced microwave devices, different kinds of the devices, the directional couplers, the phase shifters, and various filters. And a conclusion will be done at the end of this presentation. It's well known that the interaction between electromagnetic wave and material or a medium is described by Maxwell equations, and these equations use the parameters of the material, the magnetic permeability mu and the dielectric permittivity epsilon, and for the conventional, for natural materials, these parameters are definitely positive ones. What is a metamaterial? For the moment, there is no strict definition of metamaterials. There are different definitions, but each of these definitions is possibly incomplete or too strict. We consider metamaterials as an arrangement of some artificial structural elements, as shown here. It can be some dielectric inclusions or metallic inclusions, some kind of spheres, cubes, wires, spirals, and some rings, split rings, printed split ring resonators, and so on. And even some pieces of electrical circuits consisting of lumped elements, capacitors, and inductors, as shown here. This is exactly the topic of this presentation, such kind of metamaterials. And what is most important, that the structure period of metamaterials should be much less compared to the wavelengths, and if this is the case, the structure behaves as a homogeneous materials with some new effective parameters, mu and epsilon. And these parameters, under some conditions, can be negative. So we can consider double positive materials or the conventional materials which obey the right-hand rules for the vectors of electric field, vector of magnetic field, and the wave vector. And some materials or some media can exhibit the negative epsilon or negative mu, or for example, ferromagnetic materials have negative mu, and plasma under some condition as negative epsilon, but double negative materials which obey the left-handed rule when the propagation vector is in the opposite direction. Such materials can be only artificial ones. The concept of these materials was predicted by the Soviet physicist Viktor Vasilaga in 1967, and such materials are not found in nature, but nevertheless they are physically realizable. What interesting concerning of these materials? All the negative phenomena are inversed in the materials where epsilon and mu are negative. So you can see, for example, the curved lenses which operate in different way compared to the lenses made of conventional materials, and you can see the inverse Doppler effect and inverse Cherenkov effect. But the mostly interesting, this is the negative refraction. This is the conventional case of the boundary of two media. One of this media is a metamaterial one, and this is the incident beam, and this is the refracted beam. For the conventional material, the refracted beam should be on the opposite side of the normal to this boundary. And in the case of metamaterials, it's located here. It can be easily illustrated by such figure. This is the conventional water, and this is the meta water. If this is the case, we should see such a refraction, which is called negative refraction. And another interesting effect is the so-called perfect lens. The metamaterial with double negative parameters allows to realize the lens which can focus the point source to point without any theoretical diffraction limit. And moreover, such a lens can amplify evanescent waves, and this results in obtaining higher image resolution. This is an example of using such a lens for biomedical applications, for magnetic resonance imaging. You can see how it looks like without any metamaterial lens. This is a conventional MRI image, and this is the image when such a lens, which amplifies evanescence waves, used, and you can see that in this case the image resolution is enhanced. Let's now go to the transmission line theory. It's well known that there is an analogy between the wave propagation in a medium and in a transmission line. So at least for the transversal TM mode, we can always move from the equation, from the field equations to the transmission line equations, just by replacing the mu and epsilon with inductance and capacitance per unit length. So one can consider transmission line for the case of a normal or conventional material. This is the electrical length, which defines by the propagation constant or the wave number, which is shown here. And this is the dispersion law, which is linear for this case, and one can use any transmission line, the coaxial line, the waveguide, microstrip line, coplanar line, and so on. And moreover, such a transmission line can be represented as an equivalent circuit consisting of seriously connected inductors and capacitances connected in shunt. And there is a very good analogy between the wave propagation in this transmission line and in this equivalent circuit. The same can be applied to the case when the wave is propagated in a metamaterial with negative epsilon and negative mu. The only difference is that in this case, the propagation number is negative, so the propagation vector is in the opposite direction. This is the left-handed triad of the vectors. And in this case, this results is a negative phase velocity. So the phase velocity is also in opposite side compared to the group velocity. And this can be represented by such an equivalent circuit with interchanged capacitances and inductances. And the dispersion law is nonlinear, shown here, like this is a hyperbolic law. The only difference is that for this case, there is no transmission line analog based on distributed elements. There is no something like meta microstrip line or meta coplanar line. Such a transmission line can be only implemented in artificial way by using lumped capacitances and inductances. And in order to design such a transmission line, we can use the conventional theory. One can compare the transmission matrix or ABCD matrix of a transmission line section and of a pi or T networks based on lumped elements. For the conventional case, the electrical length of the transmission line is considered positive. For the metamaterial transmission line, the electrical length is negative, which is because of the negative phase velocity. So by comparing these matrices, one can obtain rather simple equations. These are two different unit cells for the conventional right-handed transmission line, the artificial transmission line, and these are two unit cells for the left-handed transmission line with such electrical lines. And these unit cells can be implemented in different ways using an integrated technology. You can see some interdigital capacitors to the ground, like shown here, and this is an inductance, and in this case, this layout corresponds to this unit cell with two grounded inductances and a series capacitance in between. And such unit cells can be also implemented using surface mount components, as shown here, for example. And of course, we can use for the transmission line of a certain length, we can use one unit cell or two cascaded unit cells or three or a large number of cascaded unit cells. And the entire matrix can be easily calculated, and so we can realize the same electrical length by using different number of unit cells. The question is, how many unit cells do we really need to implement an artificial transmission line? What is the difference? The difference is the operational bandwidth, because for one single cell, you can see the solid lines correspond to the reflection coefficient, and the dashed lines are the transmission coefficients for 1, 2, 3, 4 unit cells, and for the right-handed case and for the left-handed one. Generally, bandwidth is estimated at the level of minus 20 dB of the reflection coefficient. So for a single unit cell, the operational bandwidth is very narrow, just a few %. But if we use two cascaded unit cells, the operational bandwidth is large enough. We can see here from 0 frequency to the frequency which is nearly twice compared to the central frequency. This is the normalized frequency. And here, vice versa, from 0.5 to almost infinity. So we can conclude that for the most practical applications, 2 unit cells per a quarter wavelength is enough. And now I'm going to show you some examples of practical applications. This is the directional coupler, which is called in the literature as a rat race ring. This is a really ring consisting of 3 quarter wavelength sections and one transmission line sections with the length of the 3 quarter wavelengths. So if we use this port 1 as the input, the device divides the input power between these 2 ports, and this port is isolated. So we can see this is the equal power division. So 1/2 of the power minus 3 dB goes to one port, 1/2 of the power goes to this port, and this port is ideally isolated. And for the conventional rat race ring, the operational bandwidth is about 30%. It's mostly limited by the presence of this electrically long transmission line section. If we replace 3/4 wavelength section, which has the electrical length of 270 degrees, by the left-handed one, with the electrical length of minus 90 degrees. This is the same. The last one has smaller variation over frequency than this case, this transmission line in this case. So the bandwidth can be extended almost in 2 times. But this is, of course, theoretical figure and how it can be implemented in practice. You can see 2 cascaded transmission lines to replace this section and 2 cascaded unit cells of this kind to replace these 3 sections. So this is the entire circuit, which can be realized using surface mount components on using an integrated technology. Here we used the multi-layer integrated technology. So for inputs, you can see some parallel plate capacitances to the ground, these ones, and these are these capacitances. Some inductance are realized as here 2 turns inductors, here 1 turn inductors, grounded by using these wire holes, metallized wire holes. And you can see characteristics in 2 different regimes, because such device can provide 2 different regimes with in-phase outputs and with out-of-phase output. But you can see that in both cases, simulated and measured characteristics correspond to each other rather well, and the size of the device is quite small. This is another advantage, because this size is 6-fold compared to the size of the initial conventional directional coupler, and the bandwidth was extended in 1.5 times, so 45% instead of 30% for the conventional case. Another example, this is the phase shifter, the switchable channel phase shifter. There are 2 channels, and there are so-called single port double through switches. So in one case, the wave goes to this path. In another case, the wave goes to this path. One channel is a conventional transmission line. In this case, this is the coplanar waveguide section. And here you can see 2 cascaded T cells of the left-handed transmission lines. It allows to obtain rather broadband phase shifter with a small variation of phase, with low insertion loss in both states, and with a very good matching. And here you can see measured and simulated phase difference. This is the phase difference, which is flat enough. The same concept can be used to realize multi-bit phase shifters. This is an example of the 6-bit phase shifter. The 3 higher bits are realized using the same concept, and such a phase shifter provides 64 different states. You can see the phase shift error is rather small and nearly does not depend on frequency, and the other characteristics are also very good. More one example, the so-called signal interference filter. This is the conventional device, which uses 2 transmission lines of different lengths, and the interference of waves propagating by these 2 passes provides at some frequencies the band pass, and some frequencies the band stop response. And this conventional device uses 1/4 wavelength transmission line sections and 3/4 wavelength transmission line sections. There are 2 main drawbacks of this device. First, of course, these long transmission line sections increase the entire size of the device. And the second one, there are the spurious passbands, the parasitic ones, moreover, not at the higher frequencies, but for this configuration of the filter, also at low frequency, there is a spurious passband. How it can be improved? We can just use right-handed and left-handed transmission lines in combination. So one transmission line section is replaced by the metamaterial transmission line. And both of them are realized as the artificial ones. You can see two unit cells of the right-handed transmission line section. And here it was enough to use only one single cell for the left-handed transmission line. Again, the multi-layer realization, very small sizes of these devices, and characteristics are very good. You can see that here the characteristics go in this way, so there is no spurious passband. It was suppressed by using this design because of involvement of this metamaterial transmission line section. And I'm going to show you one more example. This is the figure from the conventional filter theory, two circuits representing the bandpass filters based on coupled resonant tanks, coupled via the so-called impedance inverters or admittance inverters. The trends, modern trends of development of wireless communication systems are towards using many different bandwidths. So multi-band filters are in high demand. And to design a multi-band filter, we need to use dual mode resonators, and moreover, the emittance inverters should also operate at two desired frequencies. Besides, if we would like to design a tunable device, so all the resonators as well as the inverters should enable tunability. And this is example of the advanced dual bandpass filters which incorporate such dual frequency emittance inverters. You can see the characteristics that two pass bands which can be placed at different central frequency and different widths of these pass bands can be provided. What is most important, there is a very good attenuation between the pass band. This is the main advantage of such filters because providing a high attenuation between the two operational bandwidths, this is the most complicated problem for the conventional dual band filter designs. And here the key point is this inverter, because you can see it consists, it's a special combination of the unit cell of left-handed transmission line and right-handed transmission line elements, and such unit cell is known as the unit cell of the so-called dual composite right-left-handed transmission line. And you can see that this inverter results in obtaining this stop band, so such filters can be designed thanks to application of this inverter. And this is an example of a tunable inverter which uses not pi by T circuit as shown here. So you can see 3 capacitances and 3 inductances. And here the 3 capacitances were replaced by the varactor diodes, and these are the 3 inductances, and all other components, this is the biasing networks which are needed to apply the biasing voltages to varactors. And when we change the biasing voltage, varactors change their capacitances, so they operate as tunable capacitances, and this results in tuning of the operational bandwidths, which can be tuned simultaneously or independently to each other. So you can see the tuning of one bandwidth is shown here by these 2 arrows, and the tuning of the second operational bandwidth is shown here. For this device, which uses these commercial varactor diodes, the tunability was obtained as 14% for the lower operational frequency and 18% for the high operational frequency. And This is an example of such a two-pole filter which uses two resonators, again with capacitances replaced by varactor diodes, and this is the same inverter. And you can see characteristics. So there are two passbands with a good attenuation between them, and these passbands, both of them, can be tuned. So this is the tuning range of this filter. So I'm going to conclude my presentation with the following statements. I will not read all this text. Thank you very much for your attention. If you have some questions, don't hesitate to ask.
Okay. There will be time to ask more questions to Dmitry, and we have to proceed.
Okay. Thank you once again.
So just a few words of the organizational character. Time has come for us to split the conference and start working in sections. If you haven't yet seen the time of your presentation, please have a look at the programs of sections. They are posted in the lobby. If for some of you there is need to change the time of your presentation, please do not address me. Ask or contact the chair of your section, because they are empowered to do all the necessary changes. Sure, it's possible to tune the time of your presentation. At 12, we'll have the lunch break. The coffee break for everybody. And at 2 p.m., there will be the lunch break. And we expect the conference to work today till 5 p.m. So again, if any organizational questions, please don't hesitate to contact me or Svetlana Pritkova. For sure, you all know her through correspondence. Or any of our student volunteers, you can recognize them, they are wearing yellow caps. So I wish you every success in your work, in your presentations. Let's move on. Thank you.